and the world's largest accelerators, 27 kilometers in circumference in one direction and 27 kilometers on the other side of the ring. Dr. Antinori has been, until recently, the leader of the ALICE project. The ALICE detector measures flow and observes thermometric signals. Yana and electron-positron pair is the center of interest for him. You have the floor, sir, and we look forward to your presentation.
Okay, so thank you very much for introducing me, and thanks first of all to Professor Bikar Singh for inviting me here. I'm really very happy to be back again in a city I love so much, where I have so many friends. And actually I'm very intrigued by the theme of the workshop, being also a fan of Tagore. So I'm really looking forward to the rest of the program. So my talk is about the ALICE experiment. This is an outline of the talk. I will start with a bit of an introduction, and then I will tell you about what the ALICE experiment is, and then I will discuss a few of what I consider to be the main results so far, and then I will tell you about our plans for the future. So let's start from a bit of introduction. The experiment is designed to study the physics of strong interactions. This is one of the four fundamental forces, and it is the force that binds the quarks inside the hadrons, such as protons and neutrons, and that binds the nucleons inside the nuclei. It is described by quantum chromodynamics. This is the theory that describes the interaction between the color charges of quarks and gluons as mediated by the gluons themselves. It is a very successful theory. It can predict, for instance, the jet production cross-section over 10 or 11 decades. Very precise calculations also are available for instance, for the production of heavy flavor, especially at the larger transverse momenta. But our understanding still is faced with some outstanding puzzles. One of them is the hadron masses. We know that a proton contains 2 U quarks and 1 D quark, and if you sum what we estimate to be the current masses, the Lagrangian masses of these particles, you get to something around 10 MeV, and we know that a proton weighs 100 times that. So about 99% of the mass of ordinary matter, which is essentially contained in the nucleus, is generated dynamically by strong interactions, but we know pretty little on how this comes about. And the other is confinement, of course. We know that quarks exist, but nobody has ever managed to observe an isolated quarks, and people have tried with very fine experiments. And indeed, it appears that they are permanently confined, so 1/2 of the fundamental fermions of the standard model happen not to be directly observable. And there are compelling arguments that this is due to the non-abelian nature of QCD itself, but there is actually no rigorous proof. The most rigorous way to do calculations in the non-perturbative regime, in the soft regime of QCD, where these puzzles lurk, is the use of lattice QCD. What you do, you discretize the theory on the quantum field theory in a space-time lattice, and then this allows to take care of ultraviolet divergences, and then of course you take the limit for the lattice spacing going to infinity. And we know that at high temperature the lattice QCD calculations predict a phase transition from the standard hadronic matter to the QCD plasma, which we call the quark-gluon plasma. I've been asked to try and be as fast as possible since I'm standing between you and lunch. So I will not go into the details of the lattice calculations, although there are a few things to notice that are actually very interesting. Now, experimentally, how do we go about this? Ultra-relativistic nuclear collisions. This is the experimental tool that allows us to compress or heat matters to the energy densities that are required, temperatures of the order of 150 MeV, to recreate this plasma in the laboratory. And with the collisions of two heavy nuclei, which are accelerated at ultra-relativistic energies, in particular at colliders, we manage for a tiny fraction of the order of 10 to the minus 33 seconds to recreate the conditions for the generation of quark plasma. And this is very important because essentially this is a tool that gives us an experimental access to the study of the condensed matter of QCD. And just like in its electromagnetic counterpart, when you go to condensed matter physics, you have a quantity of beautiful phenomena that appear that you cannot get at in practice from the fundamental Lagrangian. Even more so in the case of QCD, given that the underlying Lagrangian is even richer than that. The ALICE experiment, as I said, is designed to tackle this. No, wait, I have another one before. So I think I will skip this in the interest of brevity. What I would like to say is two things. First of all, that the higher the energy at which you study the collisions of heavy ions, the closer you get to an ideal condition that reproduces that of the early universe. And the second one is that by going to higher and higher energy, you have a larger and larger cross-section for the production of calibrated probes, in particular, as you will see, heavy flavor quarks. The ALICE experiment is made by two main components: a central barrel with essentially cylindrical symmetry immersed in a 0.5 Tesla magnet, and then a forward muon spectrometer which allows to detect muons a bit displaced from the very central rapidity. The main characteristics of the apparatus are the fact that we need to work with very low material budget because we want to track particles down to very, very low momenta, and we need to have high resolution vertexing because we want to be able to detect the decay products of heavy flavor particle disintegration. So far, we have been studying lead-lead collisions, but not only, also proton-proton and proton-lead collisions, and we also have a small sample of xenon-xenon. The India contribution is very important. India is one of the largest contingents in the collaboration. There are 15 institutes, 31 scientists, and 49 PhD students, and very key contributions have been made to the experiment by the Indian community, in particular on the photomultiplicity detector, the muon arm, time projection chamber, and of course physics analysis. You will hear much more about this in Jürgen's talk. And of course all this is in very large part due to the very inspired and enthusiastic, as you see, leadership of Bikash Singha, who has been instrumental in putting together the Indian collaboration and leading it. This I will skip. And now go to the results. Before I go to the details of the results, I have to have a little technical point. As you will see, it is very important to know how central each collision has been. And in order to do this, the experiment where central means how close the two nuclei, the centers of the two nuclei passed to one another. And in order to do this, the experimental handle that is used most often is the multiplicity of particles which are produced in a collision. So in a peripheral collision where there are where the impact parameter is very small, you have a large superposition of nucleons which collide, and therefore you have a very large number of particles which are produced. Conversely, in a very peripheral collisions, you have few. And in order to be able to use this in a calibrated way, you have to model somehow the connection between impact parameter and number of participants and multiplicity with a fine fit which allows really to follow the dependence in detail, and this then allows us to extract the basic quantity, which is a good estimate of the number of nucleons which have taken part in it. Something about the quality of the data. These are identified particle spectra for pions, kaons, and protons. We can go to even, let's say, heavier and rarer particles, K star, phi, omega, and you can see that from the quality of the data, we can very clearly follow how the particle production depends on the centrality of the collision. For instance, the red are the most central, and then little by little one goes to more and more peripheral collisions, and the black is the inelastic. You can see some changes of slope you can really judge by eye, and this of course is very precious material to study the ionization of the QGP, its radial expansion, and its result properties. An example, you can integrate these particle spectra and get the yields, and the yields are displayed in this cartoon on the left, and they are compared with what one would expect for thermodynamical equilibrium, chemical equilibrium among the species at a temperature of 156, this is 153 MeV. And you see that by and large there are important deviations, but by and large, very differently from proton-proton, the abundances of these particles are very close to those that you would expect from essentially full chemical equilibrium. And this is a representation of the strangeness enhancement. This is, of course, connected to the fact that the production of strange particles in the wormhole plasma is enhanced. And this holds even for nuclei and hypernuclei in spite of the very low bonding energy, so that actually the enhancement in the production of these particles with respect to proton-proton collision is so significant that one of the byproducts of this physics is the ability of studying the properties of these particles with very high statistics production. Another very interesting thing that you can do, you can, by fitting those spectra, you can try to extract separate information about, on one hand, the temperature at which they were emitted, but also the radial flow of the source that was emitting them. And actually, by doing combined fits, which I will not enter into now, you can essentially measure the expansion velocity of the fireball, and this is found to be about 2/3 of the speed of light, which is actually the largest that has been observed. Of course, with higher and higher energies, the speed increases, but we are essentially at the limit of the speed of sound. Another very interesting observable in the study of the properties of the quark-gluon plasma is the azimuthal asymmetry. Why is it important? Because non-central collisions where the two nuclei hit each other at a distance are asymmetric in azimuth. This is a sketch of such a collision. You can imagine one of those two circles is one nucleus entering the screen, and the other is the opposite one exiting the screen. And as you can see, the superposition region has this characteristic that shape, almond shape, and if you want to go from the center where you have the highest pressure to the periphery, to the outside where you have zero pressure, you can do this much quicker if you go through the horizontal line, what we call the in-plane direction, then through the vertical line, the out-of-plane direction. The transfer of this asymmetry from the configuration space to the momentum space is a measure of the strength of the collective phenomena. And this is very easy to understand. If you have a large mean-free path, in the limit, if the particles stream out isotropically, you will have no memory of the fact that the original source had an asymmetry, because there will be no way for particles to know. If you go to smaller and smaller mean-free path, then the particles will start to hit other particles and to gain information about what the size of their source is. And at the extreme of zero mean-free path, which is the ideal liquid extreme, you will have the maximum of the effect. And this is actually what we observe. In order to quantify this asymmetry, we use you take the Fourier expansion of the angular distribution, and you use the first element, which is non-trivial, in the expansion, which is the second order coefficient, and this is the V2, and basically this is what is plotted here, V2 as a function of the centrality. So to the left you have the most central, to the right you have the most peripheral, and you see that at least for the most central collisions you are very close to what you would expect from ideal thermodynamics. That was the second order coefficient. The higher order ones are also accessible, and actually they provide a really beautiful tool. We now have a very compact and effective way of studying the dynamic response of the QCD medium, and also of following the interaction of the hard probes with the QGP. And in fact, this type of information has allowed us to put very strong quantitative constraints on the parameters of the quark-gluon plasma in itself, which in the end is one of the main aims of this field of physics. And this is an example from a Bayesian parameter estimation, which has allowed to reach by now the measurement of the QGP viscosity with about 20% precision. And by the way, the fact that the behavior of the QGP is so close to ideal electrodynamics reflects a very low value of the shear viscosity, which is actually about 10 times less than that of any other form. Direct photons are one of the old dreams of Bcash. and also of Dinesh. And well, we are getting there. This is the latest result. The precision at low transverse momenta is still rather limited, but as I will show you, we shall get there anyway. We are not giving up on going really to the very low into the thermal reef. Now, as the plasma expands, before it hadronizes, high energy partons that traverse it interact with it, and that can also bring out information on its properties. And one very handy observable for doing this, for studying this, is what we call the nuclear modification factor. Basically, it is the ratio of the transverse momentum distribution, in this case, between nucleus-nucleus collisions and the one in proton-proton suitably normalized, because simply because of the larger number of particles which are produced, and this scales at high transverse momenta as the number of nucleus-nucleus collisions. And as you see, the lowest right is the most peripheral class in this particular plot, and then as you go to the right and then up, to the left and then up, you go to more and more central collisions, and you see that you have stronger and stronger quenching. This is shown here both at 2.75 and at 5 dB, and you see that there is actually very little dependence, although the spectra harden quite a bit with Ruther's special effect. Now, where this becomes very, very powerful is with heavy flavor collisions, because there you are dealing with heavy quarks, so you know if you have a heavy flavor particle that it was a heavy quark that propagated, and actually that it was a quark at that, as opposed to a gluon. So this gives a very powerful, calibrated information about the nature of the probe, and also about its original production, which can be calculated at least at IPT in perturbative QCD, and then the calculation can be calibrated with proton-proton collision. So the large mass of charm and beauty quarks essentially allows us to use them as sort of Brownian probes that interact with the medium and then bring out very interesting information about its property. And this is an example. Here what is shown is on the left the RAA, so the nuclear modification factor for the production of D mesons. On the right you have the V2, this azimuthal symmetry that I was introducing before. And the combination of the two is actually very, very powerful. If you look at the plot on the bottom right, this shows the